Hello! Today we would like to present the problem of optimizing the placement of MEVO bike stations in Gdańsk. Let's start with what MEVO actually is. MEVO is a system of self-service city bike rentals operating in the Tri-City area and its surroundings. This system works on the basis of stations located in various parts of Pomerania, which allow rental of regular and electric bicycles. We decided to base our work exclusively on the city of Gdańsk. Initially, we downloaded public data from the MEVO website and received a file in the format shown in the figure on the left. Here we can see information about the station such as its location and capacity. We converted the data into a GeoJSON file format, which will be needed for the subsequent implementation of the entire project. Here we see data regarding the usability of regular and electric bicycles and individual stations, which are also modified by us to suit our needs. In addition to the official data from the MEVO website, we also downloaded other information that was essential for our analysis. We obtained this data from the Gdańsk City Hall website. On the map, there is Gdańsk divided into districts which are marked with colors. The darker the color, the higher the average age of the residents. We see that the lowest values occur in districts such as Jasień and Letnica, which are places that have been significantly developed in recent years, leading to great interest from younger people. We can expect high demand for bike stations in these areas as many young people choose bicycles as a combination of transportation and activity. The next data concerns the population density of individual Gdańsk districts. Here we see that the highest density values correspond to the darkest colors. These are districts such as Chełm or Zaspa. We can conclude that there will be a greater chance that more people will decide to use rental bicycles in these districts. On the other hand, districts with low population, such as Rudniki or Wyspa Sobieszewska, can expect relatively low interests in bicycles. Next, we can see a map with marked points, which correspond to the most important commercial and tourist places in Gdańsk. Naturally, the highest concentration of these occurs in Śródmieście, especially around the Old Town, where the majority of the city historical monuments are located. Furthermore, we have placed points here in Gdańsk, where many shopping centers are situated. In this case, we assume that busy tourist and commercial areas will generate high interest in bicycles, as it is a convenient way to move around the city. Here we see another map of Gdańsk where we have marked important public transport points with green dots. These include railway stations and the most important bus stops. The points are primarily arranged along the lines of the rapid urban rail tracks in Gdańsk, which are places where potentially many people may use MEVO as a complement to their journey. At last data, we used concerns places related to employment and education. The brown dots correspond to workplaces employing a minimum of 250 people, as well as the most important educational centers, such as universities and secondary schools. Here too, we can observe that their greatest concentration occurs in central districts such as Śródmieście, Wrzeszcz, and Oliwa. For the project implementation, we used the QGIS program, which offers wide possibilities for data analysis in a geographical context. For this reason, we could easily import the map of Gdańsk with its district divisions and then perform subsequent operations, such as applying colors or points to the map which we presented earlier. Subsequently, we applied a grid measuring 100 meters by 100 meters to the map so that the function, which we will discuss more about shortly, could take different values for each cell. We obtained over 27,000 of them. Additionally, we applied centroids, which are the geographical centers of each square. Here we present an approximation of the grid at the Baltic hub. Let's move on to the function. As we already mentioned, we created a function that allows us to calculate a value for each of the over 27,000 squares, and all calculations related to these were performed in the QGIS program. We wanted the function to be dependent on each of the previously mentioned parameters, so average age, population density, the presence of tourist and commercial points, public transport stops, and the largest employment areas. Additionally, we had to consider the existing MEVO stations. We will use the d-norm coefficient here, which refers to the distance from the centroid of each square to the nearest MEVO station. We normalized these distances in such a way that the greater the distance, the lower the resulting value. Similarly, we normalized the density and the average age of residents of a given district so that the values belong to the range from 0 to 1. The formula for the function is shown at the bottom. We assume that if the distance of the centroid to the nearest station is less than 150 meters, we will not place a station in that location, which is why the function result is 0. Otherwise, the function takes the value given by the visible formula. As we mentioned earlier, we calculate the function values for each square. The higher the function result, the greater the probability that we will need a station in that square. The initial results are presented as follows. The higher the function result, the darker the color and the greater the demand for the station. Here we see an approximation for Gdańsk Śródmieście. White squares correspond to places where a station already exists or is within a distance of less than 150 meters. Darker squares indicate that it would be worthwhile to consider building new station in that location. On this map, we present the top 50 squares that received the highest result from our function. And here, similarly, but considering the top 25 results. These are the places where, according to our analysis, it is most profitable to place new bicycle stations, as the demand of them is highest there.
In order to examine whether the results of the function are applicable in reality, we checked each of its 25 highest results. We manually analyzed each location, checking whether there should be a station in the given square. In this way, we accepted 18 locations and rejected 7. The first case in Zaspa, near a hospital, we received 2 high function scores. The nearest station is located about 200 meters from the rear entrance of the hospital, and it is also a densely built-up area, So we decided that adding one station should be sufficient for this location. Most of the area indicated by the squares is located directly on buildings or private land, so we are placing the stations at the intersection of two nearby streets that are not included in any of the squares, Polonia Gdańska and Braci Majewskich. Here we have the proposed station in Zaspa in red and the existing MEVO stations in purple. The proposed location of the station in Zaspa from Google Street View. In Jasień, near Designer Outlet, unlike other shopping centers, there is no MEVO station. Therefore, we are placing the station in the parking lot between the buildings. The proposed station is not located directly in the indicated square because it contained almost exclusively buildings. Here we have the proposed station at the Designer Outlet shopping center in red and the existing MEVO stations in purple. The proposed location of the Designer Outlet station from Google Street View. And in this third case, in Przymorze Wielkie at Galeria Przymorze, there are already designed stations for this location. Based on rental data, we know that they are not overloaded. Therefore, no additional station should be built in this location. The result for this square is among the 25 highest results because we marked a retail point in it. The centroid of this square is located approximately 210 meters from the nearest station, so this grid cell does not have a value of 0. We would avoid the situation if we marked the locations of shopping centers closer to stations or used a different method of marking public utility objects. The rejected result, the square at the Galeria Przymorze shopping center, and existing MEVO stations in purple. The second method of optimizing the location of MEVO stations is the iterative application of our predefined function. The procedure is as follows. Calculating the distance of centroids from stations and normalizing the results. Then, determining the function value for each grid. Selecting the m highest results. For the m highest results, inserting stations at the centroids, and repeating the process until the pool of n new stations to be inserted is used up. In each iteration, the distances of the centroids to the nearest stations are determined, which are then added to the previously merged table. Based on this data, the function value for each grid is calculated, and then the m grids with the highest values are identified. Stations are added at the selected locations, and then the columns containing distance data are removed to avoid errors in subsequent calculation steps. The main difference between the standard method of calculating the function and the iterative method is that in the former we calculate the function for each grid cell once and then select the m highest values from all the results. In the iterative approach, we calculate the function values for each grid cell, select the m highest values where m is smaller than n from all the results, and add them to the pool of stations already existing in the city. We repeat the entire procedure until we add n new stations. In this way, new and subsequent locations are determined taking into account those previously given by the function. Thanks to this method, we significantly reduce the occurrence of several high results close to each other. In the northern part of the Kokoszki district, the function returned 4 results using the standard approach, the red squares, and 2 using the iterative approach, green circles. The main difference is the number of results and the distance between them. The second method does not indicate grids that are extremely close to each other, but rather those that are significantly distant, and it indicates fewer of them. The advantage of the standard approach is a larger selection of proposed locations for stations, where the advantage of iterative counting is a more unambiguous indication of grids. Depending on the correct precision, resources, and methods of determining variable functions, the appropriate method can be selected. The iterative method is very sensitive to the distance from existing MEVO stations. Based on the article A Hub Location Inventory Model for Bicycle Sharing System Design, Formulation and Solution, we developed a program to calculate the minimum number of bicycles needed at each of the stations under consideration, given the appropriate level of service, specifically delivery period and average daily demand. We use the following formula where lambda k is the average daily demand, tau k is delivery time, q is the number of bicycles, alpha k is the service level, and k is the station's ID. In the article, lambda k is taken as the predicted average annual demand for bicycles at station k, summing the average annual demand for trips from location A, where the station K is located, to location B and connections to other stations. With information on bicycle rentals over a 28-day period, we take their average value as lambda k. We can modify the level of service offered ourselves depending on our preferences. We assume that the most optimal solution will be to ensure the availability of facilities in 95% of cases, so alpha k is 0.95. With data on bicycle usage frequency and delivery times, we calculate the minimum number of available facilities that meet our assumptions. Stations that are more popular should be replenished more often, while those that are less used should be replenished less often. Here is the code written in R. The headers of the result tables are, respectively, the station's ID, the number of electric bikes rented over a period of 28 days, the daily demand for bikes, and the minimum value that should be ensured for delivery once a day on the left table and twice a day on the right table. We can see from this that electric-assisted bikes are very popular and frequently chosen. The table headers are the same as before, but we only consider one delivery per day for regular bikes. The left table shows stations with low results, and the right table shows stations with high results. We can see that there are stations with a minimum stock of 0, and in this case we can consider removing these stations. Thank you for your attention.